This is number 48 in chapter 9. It's looking at the Born-Haber cycle for the formation of calcium oxide. And it's asking us to determine the lattice energy for calcium oxide. And so we want to use the Born-Haber cycle in order to determine that. And so the first step would be to actually look at what is the reaction that's occurring. We are going to have calcium reacting with oxygen to form calcium oxide. And so that would be our properly balanced equation. Notice that calcium is a metal, it's in the solid state. Oxygen, normally it's in the gaseous state. And so we have these phases that we have to account for too. So with the Born-Haber cycle, the rules that we want to follow is, first we have to get each element in its monoatomic state. And so we don't have to worry about that for calcium, but we do have to worry about that for oxygen. Not only do they have to be in the proper monoatomic state, they have to be in the proper phase. So first monoatomic, second is phase. And that phase needs to be gaseous. The third step is then in the proper charge state. And so that's going to involve either electron affinity or ionization energy in order to get the proper anion or the proper cation in order to condense, which is the final step, which is the lattice energy. So we have to put all these steps together. We have to get each of the elements monoatomic, we have to get them in the right gas phase, we have to get them in the right charge state, and then we can then figure out the actual lattice energy. So if we're to begin, let's first begin with our calcium. Is calcium monoatomic? Yes, calcium is monoatomic. And so what we want to do first for calcium is go to step 2 and get it into the gaseous state. This is the delta H of sublimation. The delta H of sublimation they actually give us to be the 178 kilojoules per mole. And so we're going to have a table over here off to the right. So we have calcium now in the right phase. It's monoatomic. And so now we want to ionize calcium. And we have to do this in a stepwise manner. And so there's going to be 2 ionization energies, which they give us in the question. The first ionization energy was equal to 590 kilojoules per mole. That's to lose the first electron. And then we have calcium plus 1 that's going to go to calcium plus 2. And that would be our second ionization energy, which is 1,145 kilojoules per mole. We're all set with calcium now. Calcium is ready to react. We have it in the proper phase. It's monoatomic, and it's in the proper charge state. Now, we have to know that it's plus 2, again, from what calcium oxide looks like. With calcium being in group 2A, it always wants to be plus 2. And again, oxygen wants to be minus 2 then as a result for these guys to bind. Oxygen then being isoelectronic with neon. So we have calcium ready. It's ready and primed to go. Now we have to work on oxygen. And so the first step is oxygen monoatomic? And it is not. And so we have to take our oxygen gas and cleave the oxygen-oxygen double bond. And so in that case, I'm showing oxygen now monoatomic with its valence electrons. And so this would be equal to the delta H of the O 2 double bond. And more importantly, it would be 1/2 of that value. And we would get that value from bond energies. And the bond energy for an oxygen-oxygen double bond is 498 kilojoules per mole. Now that we have oxygen monoatomic, we then need to do an electron affinity step, where now we're going to give the oxygen 1 electron and make it -1, and so that would be our delta H of electron affinity 1, which the question gives us as being equal to -141 kilojoules per mole. And then we have to do that process again to get oxygen in the -2 state, and that would be the delta H of our second electron affinity, which in this case is actually a positive 744 kilojoules per mole. Now that we have all that, our oxygen is ready to react. We can then have our calcium +2 in the gaseous state reacting with our oxygen -2 in the gaseous state to form solid calcium oxide, and that right there is our lattice energy. So basically we need to add up all of these steps, and so to make some room and then summarize, our delta H of reaction would be equal to the delta H of sublimation for the calcium, the delta H for our first ionization energy of calcium, plus the second ionization energy for calcium. And so that is really now all talking about our calcium. And then we're going to add to that, and I'm just going to put this down here so I have a little bit more room, plus then the delta H for our oxygen-oxygen double bond, and we would take 1/2 of that, plus then the delta H of our first electron affinity, plus the delta H of our second electron affinity. And so this whole thing is dealing with the oxygen. And then lastly we have our lattice. So if we look at this question, we have all the information save for the delta H of the lattice using the tables in either the appendix or in chapter 9 as far as table 9.3. And so if we now begin to plug these values in, our delta H of reaction is really the delta H of formation for calcium oxide. And when we look that up in the appendix, we see that that delta H is -634.9. These are all going to be in kilojoules per mole, and so I'm going to leave out units for now just to help with space. And so that delta H of reaction was equal to then our heat of sublimation, which was 177.8 kilojoules per mole, plus our first ionization energy, which was 590 kilojoules per mole, plus our second ionization energy, which was 1145 kilojoules per mole. So again, that was all dealing with the calcium. And then we're going to add to it our oxygen energies. And so we would take 1/2 the oxygen-oxygen double bond energy, which is 498 kilojoules per mole. We add to that oxygen's first electron affinity, which was a -141 kilojoules per mole. To that we add the second electron affinity, which was positive 744 kilojoules per mole. And so that's dealing with our oxygen, and then we have left over what we are actually trying to determine, the actual lattice energy. And so if we bring everything over to the right, we can then solve for our lattice energy to be a negative 3,399.7 kilojoules per mole. So the Born-Haber cycle, we have to follow a number of steps. The first step is to make sure they're monoatomic. Each starting material needs to be monoatomic. Second part, it has to be in the gaseous phase. Third part, they have to be in the proper charged state. So that's why with calcium, we have a sublimation energy, we have an ionization energy 1, we have an ionization energy 2 to get it into its proper charge, proper monoatomic, and proper gas state. For the oxygen, we had to break the oxygen-oxygen double bond to get it monoatomic. Oxygen's already in the gaseous state, so we don't need to worry about that. And then we have our first electron affinity, and then our second electron affinity, again to get it into the proper charge state. We put those all together, we get our lattice energy. That is number 48.